So my name is Tim O'Brien. I'm the Director of Strategic Development for Public Safety for BIRD. And we'll talk a little bit today about what you do for in-building coverage for public safety. What are some of the ways to provide that? So first of all, I think most of us know, radio coverage and the way it's typically provided. You have your donor site and provides macro level coverage, and overall, when everything's designed right, you have pretty good communication. However, when you have buildings, they can pose a problem, and especially more and more so today, as we have new green building materials. The green building materials a lot of times have metallized window coatings, additional insulation, and these really cause issues with signals propagating into the buildings. Obviously, this has been a problem for a long time with subgrade, basements, that kind of thing, heavy concrete. But now we're seeing it even in, high rise with, lots of windows. So it's becoming more and more of a problem. And so, we need to solve that issue. So there's a number of different options you can use. First is, just basically providing that coverage with the base station and running what we call a passive DAS off of that. So, attaching coax and antennas to a high-powered base station output and running those throughout the building. This works rather well, and you have that dedicated capacity. However, for the most part with land mobile radio, capacity is not usually the driving factor. And the drawback to that, of course, is you need that wireline interface back to the core network. So sometimes what is used is an LMR repeater, and we need to be careful here because the word repeater is used in a lot of different ways. The way I use it here is in terms of a LMR repeater that basically repeats back the downlink signal to the uplink. Basically provides talk around capability. And again, this is sometimes a good solution, but it also has its drawbacks in terms of its challenge to get the communication back out to other areas. So then we get into an area we'll cover a little bit more in detail, and that's signal boosters, also called BDAs or bidirectional amplifiers. And then for larger venues or venues that already have extensive fiber, possibly using a fiber DAS. So it's pretty simple, how the signal boosters and DAS help us. Basically, you put a donor antenna on the roof of the venue, install a signal booster. Signal booster has amplification both directions. And then you put service antenna or service antennas, coax and series of antennas inside the building to provide coverage. Basically, the whole idea is to make the building or other obstruction invisible to the RF signal. So maybe a little basic, but the question comes up, what is a signal booster? And basically, it's a device that amplifies signal in two different directions, but without changing the frequency, without demodulating, without moving from one frequency to another. There are devices that do that, frequency translating repeaters, but there's challenges with those in terms of spectrum ownership, and it's just a more complicated device. So we'll talk a little bit about some of the different options here. So the first option is Class B signal boosters. A number of years ago, I think we're going on 8 to 10 years ago now, the FCC reclassified and made two different classes of signal boosters. The first, which was a Class B signal booster, industrial Class B. The second was a Class A. The main delineation between the two was the pass bandwidth for the filters. If the filters were more than 75 kilohertz in bandwidth, they classified as a Class B signal booster. Less than makes it a Class A. And there's slightly different rules for each and different benefits or drawbacks to each as well. The major benefit of the Class B signal booster is its low delay. So you don't have to put a lot of thought into isolating the outside signals versus the inside signals. When you have too high a delay, you end up with overlapping signals and intersymbol interference, which distorts the signal. So the Class B signal boosters don't have that issue. They typically use analog filters. I know we say 75 kilohertz and wider is Class B, but typically due to the analog filters, we're talking several hundred kilohertz or several megahertz. For our SB2 Plus, which is a Class B booster, we offer it in the UHF band 700 and 800. And UHF includes the T-band. It's all a modular design, so that supports customs. You'll see in a minute, UHF is certainly, the way the band plan is done, demands a lot of time custom solutions. So we have two different configurations. One, a small clamshell type that's for 700 and 800 or 800, and the other for dual band and UHF is a larger version. I won't go through all the details, but basically we have a lot of features built in, monitoring and control and alarming. I will point out oscillation detection and management. That was another thing that the FCC mandated in their rules, that boosters need to have oscillation detection management, because they're running into a lot of issues with boosters both incorrectly installed and poor quality signal boosters that would oscillate, and that oscillation would raise the noise floor and basically wipe out or degrade an entire site, so cause major problems. So what I mentioned was, the modularity of the design, and we were actually able to certify, different modules within our booster, so we can do this modular design. Allows us to do lots of different configurations, whether it's rack mount, whether it's, 4 different frequency windows. I mean, we've done up to 8 different frequency windows, because of the way the UHF band is done. You have basically separate windows for 450 to 460, 460 to 470, and then you have the T-band in 6 megahertz increments. You can have separate windows for each of those. So some of these get rather complex. Based on the idea of customs, we came across another requirement where initially we looked at our SB2 Plus family to solve this issue. But the idea was, as smart meters have become more and more prevalent, we had some areas, apartment buildings, that kind of thing, where you had a lot of smart meters deployed, but they were in places where the RF could not get, like this picture of all these smart meters in a basement. They put them in the basement and then retrofitted with the smart meters later, not really realizing that you're not going to be able to communicate to them without going down in the basement, which defeats a lot of the purpose of the smart meters. This kind of illustrates the problem a little bit. Obstructions and being below grade causes for these smart meter. So we like I said, originally looked at using our SB2 Plus, but that was really meant for, a lot of different frequencies, has a lot of features in there for alarm reporting, for NFPA compliance. And so we use the modularity of some of our products to come up with a more focused smart meter repeater. It also had flexibility to change frequencies, as per the requirements of the customer. Like I said, they needed some programmability, some narrow filtering, but they didn't need a full channelized Class A booster. Additionally, we expanded, I talked about, for a general repeater or BDA, that can cover a fairly good sized building. However, once you get into larger buildings, campuses, that kind of thing, you're either going to have to add additional signal boosters for each building or each set of floors, or you're going to have to do another solution. Adding additional signal boosters is complex to balance them all, so you're not blasting a lot of noise back at the base station, and then you have multiple different systems. So that's where a DAS, or in this case, fiber-fed repeater comes in. So this is our solution that kind of does that. It has a NEMA 4 NFPA compliant head end that links to various remote units over fiber. We took what we had from a lot of our fiber DAS, the fiber transceivers that already had very good performance, and integrated them with some of the high performance RF components in our SB2 Plus. So here's some of the specifications. We're about 2 watts out of each remote unit. The optical link budget, how much fiber loss you can have, is up to about 7 dB, which, you're at about a half a dB per kilometer. So that gives you, 14 kilometers or so of distance to cover, or a bunch of different fiber splits, splices, that kind of thing. Here's just a basic view of, what a fully NFPA compliant fiber system would look like. Obviously each unit having to have battery backup is probably the most onerous request. So I mentioned that, you've got 2 different types of boosters. The one is the Class B. Class B not only, does it have some restrictions as far as the FCC goes, they're in very crowded RF environments, you have some degradation of the signal. If you have 100 signals and you only care about one, and all of those 100 signals are passing through your booster at the same level, then you can expect to only get 1/100th or 20 dB down of the power. Now that's an extreme example, and typically you do things like aiming antennas and some pre-filtering to limit that, but you see what I mean. So in those crowded environments, a Class A signal booster can be very helpful. It allows you to basically filter out only the signals that you want to pass. And we do this by utilizing digital filters. So you take the signal in, you change it from analog to digital, and then you do some programmable digital filtering. It's digital signal processing, basically a form of detailed averaging on each signal that you're interested in. And in result, you get the signal back out without the signals that you were interested in. That drastically oversimplifies it, but basically you are attenuating the signals you don't want. here it kind of shows you a little bit visually the ideal. You set a channel filter around each of the signals of interest, these in green, and you make it as sharp as you want, and it rejects all of these ones in red. And again, I can design a digital filter to have 60 dB of rejection, 20 kilohertz away. However, it comes at a cost, and that cost is the delay that we mentioned earlier. So typically, some compromises need to be made, and that compromise typically becomes widening out the filters or reducing the rejection of those other signals. And so what you get is when you have a lot of adjacent signals or nearly adjacent, you may need to widen out those filters to cover all of those or a portion of those, while still trying to reject the signals that you don't want. That points out some of the importance of having a lot of flexibility in your digital filter setups. Being able to very specifically tell how wide you want the filters, how much rejection you want, where if you have two course of adjustments, you may still be letting through some of those undesired signals that will rob some of your power. Additionally, there's some circumstances in which, the spectrum is so crowded and you have so many signals to pass that you may need to set it up wideband, which basically gets used as a Class B booster. When we actually certified ours, we were able to certify it as a dual mode, Class A, Class B, basically convertible booster between the two. The user is given a note to say, that you're changing to a Class B.
Hey, Tim, just want to let you know we've got about 2 minutes left, and we do have a question.
Okay.
The question is, when you say running multiple BDAs in a building, can you clarify if you're suggesting running BDAs inline or multiple BDAs with multiple donor antennas?
Yeah, so that's a great question. I mean, either of those is an option. Either of those you have some potential issues with. When you attach some daisy chain, in line, you need to be very careful that, anytime you repeat a signal, you're basically degrading it to some extent, adding noise in both directions. Similarly, when they're in parallel, two different donor antennas, that's an option too. And I've seen both done. You just need to be careful. It needs to be set up. System engineering needs to be done to set them up very carefully.
Excellent. And would you be able to show your contact info? We've got to wrap it up. So if anyone wants to, they can contact you for more info. You're also welcome to put your contact info in the chat window.
Okay. Yeah, I'll put it in my chat window. I don't have it on a slide. So.
Okay.
Okay. Well, thank you very much.
All right. Thank you, Tim. We appreciate your time. Great info. It's certainly an industry that has a lot of attention and focus on it right now, and deservedly so. So if you want to stay in Exhibit Hall B, the next presentation will start in less than a minute from Panorama Antennas. Otherwise, I put some links in the chat. You guys can click on those links to jump to other areas, be it the classroom, Exhibit Hall A, or the meeting room. If you want to go over to the auditorium for that session, you'll still have to do that manually. Otherwise, thank you everyone for your time, and